Thank you so much for your kind introduction. So you see a lot of logo on this first slide because yes, I am responsible of innovation for Institut Optique in France. But we have also some specific initiative for Nouvelle-Aquitaine, which is a hub around the quantum technology, which is called Nikitski Center. We work, for example, with Toptica, with Excel, etc., which are located in Nouvelle-Aquitaine. And as IOJS, we are also in charge of a special governmental plan for securing lasers in France with this European partner. For example, we also work with Toptica on this subject, and this is the program Atom Control, which you can see the logo of this program, which was launched 1 month ago, and which is 15 millions for lasers in France during 5 years. But today, what I want to emphasize is that there are many technologies which are involved in quantum, and photonics are nearly everywhere in quantum computing. So statement is that optics and photonics are, of course, core technologies of quantum since the beginning of these technologies. And we do believe, especially in Nouvelle-Aquitaine, where we have a lot of people involved in lasers and fibers, etc., that quantum technology presents various innovation opportunities for the optics and photonics community. So there is still a gap between the laboratory and the market, but the photonics ecosystem has a true key plan to do to build this ecosystem. So the questions I'm going to try to answer is, who could be the key players, what is the reality of this quantum market, and how to build together a pairing photonics market. So we are going to speak all this afternoon of quantum computing. So very briefly, I will report of what is the interest of quantum computing, there are classing of problems which are exponentially difficult to deal with. For example, the famous Shor factorization of algorithm, and there is a considerable potential applications of this new technology of replacing bits by qubits, for example, in material science, condensed matter, protected communication, etc., optimization problem in pharmacology, the traveling salesman, etc., and the power of the quantum computer comes from entanglements, but in weakness from the fragility of superposition. So depending of the technologies that you are going to use, for example, so you know these technologies, there are atoms, there are ions, superconducting, hybrid, molecular, color center, photonics. We all love photonics, so maybe it will be our preferred. I'm going to speak about this. And to do these quantum computers, we need some key enabling technology where you can find cryo, control electronics, but also photonics. First of all, we do like photons. So building a computer with photons, it was a dream less than 1 decade ago, and it begins real. So we have the pleasure to have our colleagues from QUICS today. So Quandela in France, QUICS also, and there are many ways to produce these photons and to detect them. One of them, of course, is quantum dot technologies, which is developed by C2N or Quandela, but also SPDC, which is used for other technologies. So for these solutions, quantum computing with photons, you need single photon sources, single photon detectors, and photonic integrated circuits. But there are also quantum computing with atoms. We have champions, I think, in France with Pascal. So this is based with the use of neutral atoms as qubits. The particularity of this technology is that this is not really computing, because for the moment it's difficult to implement some algorithm on this, but we are more or less on simulations. This means that you need to pick up some neutral atoms like rubidium, cesium, or strontium, etc., ytterbium for other competitors, and to manipulate it with lasers, very low noise lasers, and to simulate quantum algorithm with this kind of lasers. So this is clear that with this technology, lasers and special modulation bricks are very essentials for this quantum computing platform. But this is also the case, for example, for ions. In this really nice publication, so 2021, you can see an ion which is floating through lab on chip with fiber optics. So for manipulating these neutral atoms or ions, you need a lot of lasers. And for example, in this very nice photography, you can see that you have lasers, but they are linked with fibers. So I think that we have to work on integration, photonic integration, but also coupling with fibers. So this is the case for atoms, this is the case for photons, but this is also the case for ions. And what is special with these platforms, which are ions or atoms, is that you don't choose if you need I don't know, 1 micron or 2 micron. No, this is the nature who decides what you need, and the nature didn't decide that every atoms work at the telecom wavelength. So you have to develop special wavelengths with extreme stability, agility, tunability. So there is a lot of work on lasers to do for these particular platforms. And this is surprising, but it is also the case for example, with supraconductor. In this example, you know that for example, Google or IBM work with this oldest technology, with this supraconductor, and to support the RF on the bus of this on the qubit, you can use photonic link and impress the number of qubits which can be read on a superconducting qubit using a photonic link. So you need also on supraconductor some photonics. And of course, if one day we manage to have some quantum computer which work very well, we can dream of quantum internet, and then we'll have to work on nodes and some to make speak two computers together with fibers, but also with intermediate nodes such as quantum memories, for examples. So some requirements for near-term technologies for photonics on lasers. So we have to work on power, wavelength range, no noise, etc. Swap requirements on lasers. We have to work on our sovereignty for components in free space, but also fiber, crystal, diodes, etc., etc. We have to work on advanced optical detectors, higher efficiency telecom detectors, but not only at telecom wavelengths, as I mentioned before. We need larger detectors for space, for examples. Integrated photonics will play a key this will be a key enabling technology in the future to miniaturize these computers with new production facilities, cryogeny compatibilities, loss reductions, source detector, etc., etc. And of course, on the longer term, I do believe that we have to work on single photon sources and detectors. Of course, if we must deploy it as computers from today, we have to work on the cost reduction and also to sync foundry fabrications for integrated photonics. I would like to mention that since October 23, quantum technology is considered as dual use. So this can be for our colleagues from Photonics a problem, because we think that there is not a fundamental lack of supplies, because Europe is the home of the best suited lasers or photonics. This is what we believe. And we serve maybe 60 or 80% of the current global market. But there can be a fundamental discrepancy between expectations of quantum customers and swap requirements, of course, and maybe a lack of realism on the market size. And today we must mastering with a small volume today by testing the quality in limited series and maybe preparing a ramp up. And we need non-European markets. Capital investment is needed, not only from government, but we need to increase these implications through European contracts. Thank you. It was what I wanted to say. Yeah.
Okay, thank you very much, Johan. That's a very nice summary. I see already there are questions in the audience, and yeah, I think I keep my question for later. For now, I give the word to Stefan from Quix. Please, Stefan, what's on your mind?
Yeah, Johan, thank you very much for the nice overview, and thank you for putting Candela and us in your talk. That's nice to see the heart of photonics in our process in your presentation. However, I have a question on the single photon sources. So actually, what are your plans in future? Quantum dots, down conversion sources. So how broad are you going to tackle this challenge?
That's a good question, and I think two answers. I know maybe you have more insights on this than me, and this is still, I think, an open question. My mind is at quantum dots because you can announce maybe the photon, and it is more easy to couple this with electronic, with maybe this can be the best solution. But certainly there will be other options that will be opened in the next years. And for me, the right single photon sources or integral photon sources is not yet on the market. What's your opinion on this? Tell me from Quix overview.
I will come back to this. That's still an open race, still an open question. So what we need are indistinguishable photons. And I mean, from the view of the end customer, it doesn't really matter where these photons are coming from. I need really a deterministic single photon source, which is scalable. That's the challenge currently. And I completely agree with you. There are multiple ways. We are, of course, betting on integrated photonics just because of the scalability. So the dots are great. My current impression is that it needs another decade to bring the dots to a really scalable approach, and also show that a few of the dots can emit indistinguishable photons, sorry. So yeah, maybe the dots in a decade, but for now, I mean, it's clear our bet is also on integrated photonics.
Thank you for your insight. That's good.
Yeah, scalable source of photons is indeed one of the bottlenecks I can see. We have a comment also from Luca from the European Commission, actually. Please go ahead, Luca.
Yeah, I think Mirella was before me.
Okay, sure.
Anyway, I will make a very quick question. Thank you, Johan. You say that there is no fundamental lack of supply.
Yeah.
Yes, okay, but what about the raw materials? I mean, okay, for the components, but maybe not for crystals and basic components. And what about raw material? If you can say a sentence about this. Thanks so much.
Yeah. One sentence, you're absolutely right. We don't have neobats, lithium neobats. We don't have maybe the LBO or BBO or growing of nonlinear crystal, etc., etc. And we must have a significant effort on raw materials. I do agree.
Okay. Any suggestions from the audience for the raw materials? Okay, I'll let you think about it.
Yeah, this is Mike. Yes. That we have significant investigations in creating substrates that support quantum technologies and these single photon quantum sources. There's a lot of work occurring in Berlin, specifically at IKZ Institute, that may be of interest in regards to the question from the European Commission. Thank you.
Okay.
Thanks for this. Yeah, well, as already introduced by Luca, Mireia, do you have a question? Mireia Koleva from Quantoptical. Just need to unmute.
Sorry, this is not Mirella, this is Gabi. I agree that it's currently the state of the art of single photon integrated single heralded single photon sources or probabilistic photon sources is much more advanced than quantum dots, but quantum dots hold also quite big advantages of, for example, for quantum communications. So the future will show whichever will be the winning platform, but we shouldn't ignore the potential of quantum dots. Thank you.
Okay, yeah, I can agree with this. That's a good note. Yeah, in the meantime, still no suggestions for the raw materials like lithium niobate or non-linear crystals for the European supply chain. Amir,
can I ask
come
a
on.
question? Yeah. So what do you mean we don't have this material? I mean, now there is like a dozen fundraisers at least for lithium material, like lithium niobate. So when you say we don't have the raw material, what do you mean exactly? Like I mean, SNSPDC sources are now like sort of now being commercialized as well.
Yeah,
you can find it in like sort of TFLN as a foundry service. And
I may mention maybe that, for example, to my mind, we don't produce. We need for. I speak of my specialty, but these are lasers. And for example, you have often rare earth doped fibers or crystals, and the raw materials for this is erbium, ytterbium, thulium, and I don't think that we produce it in Europe. And at one moment, it can be a problem that not to have these raw materials directly from Europe. But I don't have maybe the global overview. Tell me.
I mean, rare earths are like ions. I mean, you're talking about like sort of different things. I mean, we should not mix apple and orange. I mean, that's a different thing. Like, you're talking about like sort of rare earth ions and lithium niobate and then crystals. I mean, and always the question on the other hand is like a volume. I mean, I don't think like in a quantum is like sort of is consuming stuff at the volume that actually even matters. I mean, you have plenty of stock already in Europe and suppliers. I mean, it's not like a telecom that you're like consuming like millions of this in a year. So I don't think like for practically it's a good wish to have, but I mean like honestly like I want to put my let's say pragmatic hat and say like we have pretty much like I don't think that's really a raw material is a bottleneck in quantum in my opinion. Like it's just a performance is really a bottleneck.
So just in 2 words, what can lithium offer in this sense for the lithium niobate?
Well, I mean, like so we can offer actually sort of thin film lithium. I mean, like we are setting up a sort of company to offer thin film lithium niobate as a foundry service, and sort of to all community, and sort of sources such as SNSPDCs are available now, modulators, things like that. Laser single photon sources is a different game. But yeah, so entangled photon sources is something that definitely we can actually offer to the whole community.
Okay, thanks. Yeah. So if that attracts your attention, please, come to Amir directly or through me. Maybe that was enough for discussion for the first talk. So let's keep up with our agenda. Let me introduce. Let me thank Johan again for the great talk, and I introduce the second speaker, who is Stefan Spalter, the director for product management and quantum technologies at Toptica. And his talk is about evolving laser system solutions for quantum computing. Stefan?
Hi, everybody. Can you hear me?
Yes.
Great. Welcome, everybody. Have a great afternoon. Yeah, my talk is about evolving laser system solutions for quantum computing. And I'm leading the product management team for quantum technologies in Toptica. Maybe just for those who maybe have not heard about Toptica yet, so a few key figures. So our technology is focused on various different laser systems. So this includes diode laser systems. We are offering ultra-fast picosecond, femtosecond fiber lasers. We are offering optical frequency combs. Our offering includes fiber lasers and amplifiers. We have products on terahertz generation. And then also we are offering high power laser diodes, so we at a component level. By the way, also isolators. Some key figures, so company is 560 people strong, revenues in the order of almost 130 million, and we are around since almost 26 years now. We have a global presence with the headquarters here in Munich. And then we have different Toptica daughter companies distributed in US, Japan, China, and France. And we have other daughter companies focused on different products, like here the component business, and here this is more our astronomy branch, focusing on astronomy solutions. Now, when talking about the markets, so we have 3 market segments that we address. So the first one is in biophotonics and microscopy with multiple applications. I won't go into those now. Another market that we are addressing is measurement and processing. So this is about semicon inspections, for instance, holography, lithography, material processing, and monitoring. So yeah, all around measurement and processing. And the last one, and this is the one that is of interest here today, this is about quantum technologies and spectroscopy. And yeah, one of the prominent applications that we see there is quantum computing. And this is what we are going, I'm to talk more about what are we offering and what are we looking for also from the community. I mean, I'm very sure you're familiar with the different qubit systems that are around for quantum computing. So this can be superconducting systems, this can be color centers in solids, as we discussed, this can be photonic devices, it can be ion trap systems or neutral atom systems. And the focus of this talk will be on the ion trap and neutral atom systems, mainly because, and you will see this because of the many lasers that are needed there, and also the special requirements that are needed there to the lasers. Now, let's talk a bit in more detail about the requirements for such ion and neutral atom-based qubit systems. On the left-hand side, you see here some exemplary qubit systems. So this can be ion-based systems like terbium plus, calcium plus, strontium plus, barium plus. And again, this is exemplary. There's also neutral atom-based systems, either based on strontium, can be rubidium, strontium, Rydberg, rubidium Rydberg, or can be ytterbium lattice. So there's all types of different qubit systems. I don't want to go into the level schemes, but if you look into them in more, if you looked into them in more detail, you would see, yeah, there's many different laser transitions, also with very different requirements to those lasers in terms of power level, but also in terms of frequency stability and with respect to line width. And looking at those parameters, so first of all, looking at the wavelengths that need to be covered, there's many different wavelengths that are needed, ranging from the UV all the way up into the mid-infrared. Looking at the power levels, what we see as requirements ranging from a few milliwatt or even in the milliwatt range up to many or at least a few watt. Frequency stability, again, depending on the transition that is addressed, it ranges in the range from hertz to megahertz. Line width requirements similar. For some of the lasers, especially for the gate lasers, so the qubit gate lasers, phase noise has to be very low. And another requirement that we often see from customers, especially if customers want to move more to commercial applications, is convenient control. But even in a university environment, this is key because systems are getting quite complex, so you want to have a convenient control of the systems. So that's for the requirement side. Now let's look on what Toptica is offering. So first of all, we address this need for many different wavelengths and are therefore flexible whenever there's changing requirements or new requirements on the transitions. So even for a given system, these can change. So because customers, they tend to change then the gate laser, for instance, from different gate laser configurations. So all wavelengths is key, and we are addressing that with our highly coherent tunable diode laser systems. So those can be non-amplified systems, it can be our amplified systems, it can be the combination of amplified and frequency doubled, or even quadrupled. And so that gives us then the wavelengths in the blue at high power, or even in the UV, depending on the exact requirements. Another offering, and that's rather new, probably you have heard about our acquisition of formerly Azurelight systems. So with them, we got into our portfolio high power amplifiers and fiber lasers. So that's great. It just boosts the power that we can get out of our lasers. And another portion of the portfolio is, and that is needed for ion or neutral atom-based quantum computing systems, you need stable frequency reference systems. So this can be either a wavelength meter, it can be a spectroscopy cell, it can be a frequency comp, or it can be an ultra-stable laser, or some cavity solution that stabilizes the lasers. Now, what do we see as a trend? We see a trend towards complete laser system solutions. So customers, they don't want to bother really in integrating individual lasers, but they want to have a complete laser system solution. So typically, these should be 19-inch rack mounted and fiber coupled. And fiber coupling then ranges again from the UV wavelengths all the way up to, at least to 1770 nanometer, can be even higher in some of the cases. The system should be rather modular, so that you can mix and match different types of laser solutions. It is supposed to be fully integrated, and that's what I actually mean by complete. So it should be integrated and frequency stabilized in the end, so that customers don't have to bother with the frequency stability any longer. And then we talked about convenience before. This is enabled via full remote control and user-friendly interfaces. So that in a nutshell is what we are offering in terms of complete laser system solution. And another trend that we see is customers are looking for miniaturization, and we have done here a nice development in our Eagle Yard branch, focusing on mini ECLs. Yeah, so that's in a nutshell what we are offering as Toptica as a product. Now, where can the ecosystem help us? So one topic is actually mentioned already here, and that's the fiber coupling. So fiber coupling is a key topic for us, essentially because we need to deliver the light to the customer's experiment, and the most convenient here is fiber coupling. But especially further down in the blue or even in the UV, there's not really good and high power tolerant fiber coupled solution. So anything in that direction would be of great help for us. Now, I want to give you an example of such a complete system solution that we have been shipping and that is operating today at the customer's premises. So this is a strontium Rydberg laser system solution for a quantum computer built up at the University of Stuttgart in the framework of QRIT Demos, which is a German government-funded project. And you see, the system comes with many different lasers. So it's a total of 16 different laser systems. Actually, some of the lasers are double, so it's even more than the 16, but it's 16 different laser systems, quite complex system. And you see here the complete laser system nature. So lasers, depending on the exact requirement to that specific transition, they are locked to a wavelength meter. Some of the other lasers are locked to our frequency comb. And in turn, for long-term stability, the optical difference frequency comb is locked to an ECDL, or actually for line-width narrowing, it's locked to an ECDL, which is again locked to an ultra-stable high-finesse cavity. And that gives like COM teeth for the complete spectrum in the range of 1 or to 10 hertz line width, so super narrow line width. And yeah, so this is just an example from last year, so in which Tilman Pfau and his team, they trapped atoms by using optical tweezers. And that already completes my talk. Thanks for listening, and I'm looking forward to the discussion.
All right. Thank you, Stefan, for the nice presentation. Please, everyone, prepare your questions. You can just push this raise hand button in the bottom of your screen and I give you the word. In the meantime, I'm curious, Stefan, so you're showing all this laser systems in several racks, and how do you see the possibility to integrate this in the future, and how quickly those racks will become basically chips, or at least become size of a integrated circuit?
I think we will see those getting smaller for sure over time. But I mean, you saw like the wavelength range that we are covering today, and I've not shown the details of the level schemes, but there is schemes which require blue laser systems. And yes, I know that there's technologies out there and for integrated photonics, which we try to reach these wavelengths, but you have not really seen the power levels needed there, nor really the long-term stability in the blue. You know that there's material degradation happening. So there's certainly a challenge. So we see this full integration for all the different wavelengths still a way down the road. But yes, it's certainly something we are going to see, especially for individual wavelengths.
Yeah, exactly. Maybe more of a application-specific system that would be smaller, at least tabletop. That would be very exciting to see, I believe. One comment from Luca from European Commission, please.
Sorry, first, sorry to be in dark, but we have sunshine in Brussels. This is very unusual, but sunshine coming from the window.
Yes.
So The question is, 2 years ago, we had another epic meeting on quantum technologies, and it was announced that the brightest fiber single photon source had the 7% efficiency coupling, 7%. At 4 megahertz with a cryostat at 4 Kelvin. This is a note I have taken from the meeting in 2022. And you mentioned that fiber coupling is critical, is very important. Can you say where are we now with this coupling with the fibers?
So first of all, I should say the fiber coupling that I've been referring to is not for single photon sources. So it's maybe a bit of a different use case. So it's not that challenging from a pure coupling perspective, but the challenge is more in the material degradation that we see, especially at high power. And so here we are essentially looking for solutions. So coupling is not the real issue. So we get to decent coupling efficiencies. I mean, yes, they get more challenging in the blue, but typically that's not the limiting factor. So it's again, it's more about the material, long time sustainability, let's say. I don't know if that answers your question, Luca.
Maybe if there is a Quandela here, they can answer, because Quandela was the Quandela France, I think was the person talking about this coupling. We will see. Thanks.
Yeah, thanks for the question.
Yeah, thanks for the question, and thanks a lot, Stefan, for the talk. I don't see, unfortunately, anyone from Candela. Normally, they should be around. But yeah, if you like, we can always ask this question to them after this meeting. Thanks, Luca. Yeah, with this, I'd like to introduce the third speaker of this session, is Stefan Hengesbach, the CEO of Quix. Stefan, good to have you with us.
I'm here.
Yeah, so whenever you're ready, please share the slides. Okay.
Oh, well, actually, do you see the full screen?
Yes, we just see
Perfect.
we just see some apps at the bottom, but other than this, it's good.
Oh, now they're done, hopefully.
Good. Yes.
Wonderful. Okay, then we can start. So it has been a while. Thank you for the invitation here. It's been a while since I have been on the last EPIC meeting. I remember roughly 1.5 years ago, there was some, and we were 10 employees. Quix Quantum has evolved since then. We are roughly 40 employees, meanwhile, with offices in the Netherlands. Still, the headquarters is in Enschede, but we have also offices in Amsterdam and in Germany and in Stuttgart, where I'm currently here, and in Ulm. And brand new, we also have a new letterbox in London to have some activities in the UK going on. Topic for today is more or less Quo Vadis photonic quantum computing, where we are and what you as EPIC community can do for us. And so far I've heard the right buzzwords: fiber coupling, single photon sources. That goes into the right direction. These are indeed the challenges that we have. And our vision is to build a universal error-corrected quantum computer until 2027. So the demonstrator should be ready until 2027. And it's really not about the number of qubits. It's not about if it's 8 or 64 or 128 or 1,000. Photonic quantum computing is the only platform where the information carrier actually is moving. So we have trapped ions, neutral atoms, where the qubit is more or less located statically in a trap or under vacuum or wherever. Here, encoding information into photons is a quite nice idea because that scales very well. You can see already this nice rendering on the left-hand side is a 64 qubit system. And if you count carefully, you will find 64 of these yellow light guiding fibers that go to the core processor, which is in here. A few pumping lasers. So as mentioned from Toptica, lasers are, of course, the core pumping element here in the photonic quantum computer. We have cryostats for 2 to 4 Kelvin, where the detectors are in, some control electronics, and that's it more or less. Most of the technology operates at room. temperature, unless the detectors, the SNSPDs, are still under cryogenic conditions. But it's only 2 to 4 Kelvin, not 20 millikelvin, if you compare it to superconducting qubits. And that's in principle the modular approach that we at Quick Quantum are taking. The core element is the processor in the middle that can have multiple architectures, but it's a huge interferometer where photons can interfere with other photons. A few components are not in the sketch here. Of course, we have delay lines and we have phase shifters, which is indicated by these gold brackets that you can see. So everything our photons should do is change their phase and interfere with each other. And you can show from that you can build a universal quantum computer out of this ability to interfere and to change the phase. So the processor, that's a product that we are selling since 2019 when the company was founded. The detectors we buy, so it needs SNSPDs, and there are great companies across Europe where we can source these SNSPDs. And these are indeed under cryogenic operation and conditions. We think a quantum computer in photonic will always be modular. So you will find a lot of fiber interconnects here. And we don't have a big problem with fiber connections because we are using silicon nitride. Moreover, we use a very specific mixture of silicon nitride. We use triplex. These are 2 layers of nitride and a layer of oxide. And by changing these dimensions, we can adapt the refractive index of our material so it fits very well the refractive index of a light guiding fiber. So per definition, or in this case, due to these tailored specifications, the coupling losses can be quite low. And if you then introduce also tapers at the end, then you can also match the mode of the fiber and the chip. So we follow this modular approach because we think it's the best scalability. And the bottleneck is on the left-hand side. And these are the photon generators. And as mentioned before, they are quantum dots, they are down conversion sources, and they are so-called squeezed light sources. These are the 3 different types of sources. Quantum dots and down conversion or heralded single photon sources usually create single photons, and you go for dual rail encoding or other types of qubit encoding, whereas squeezed light generators produce a bunch of photons where you can, in principle, do better error correction. So in theory, you can do this. So there's plenty of room for the sources. And indeed, this is currently also the bottleneck. This is just one very, very basic example for how a quantum computer completely based on photonics work. You have all seen the gate-based model from superconducting qubit quantum computers or ion-based quantum computers. And what we actually do is we create a big cloud, so-called cluster state of entangled photons. And entangling photons you can do just with a beam splitter. So this is why we have so many beam splitters on a processor, honestly. So this is for creating the entanglement. Then we have the ability to delay at least one channel or multiple channels, and when we can delay by 1 clock cycle or multiple clock cycles such a photon, and then send it back to another beam splitter. And therefore we can do also entanglements over different clock cycles. And that becomes a very complex cluster state then. So for a 1,000 qubit calculation, we don't need 1,000 input ports. We can also use 100 input ports and just add 10 times a time multiplexing. And this has been indicated by these yellow fibers below the chip. So at the end, we can take a few photons off and entangle them with the next clock cycle of photons coming. And this is a quite mighty trick in photonic quantum computing, where you can save a lot of hardware in the end. So the steps for doing calculations on a universal photonic quantum computer are: we create this large entangled cluster state, we apply at the end single qubit gates, and depending on the measure of these qubits, we have to make decision and change the value of a few phase shifters. And this is called fast feed forward. This is the second really fundamental ingredient that you need for a photonic quantum computer. You need the sources, the interferometer, and then at the end, these fast feed forward. And depending on the measurement, you change more or less a few phase shifter values and then go ahead. And this architecture is quite how to say, quite convenient, because the main and dominant error is not really dephasing, decoherence, or noise, it's photon loss. And this is something that you can detect quite easily. In the end, you will just figure out that a few of your photons are missing, and then you can repeat either a gate operation or measurement and go ahead. The clock speeds are very high, a few hundred megahertz. I mean, if we ask Toptica what the repetition rate of their fastest laser is, we end up in the gigahertz range. So you can have these clock cycles of photons coming in here very, very fast, and also repeat a few operations. Where we are and what actually the current challenges are. So we have the chip. This is a product since a few years, and we have sold, I think, 15 to 20 are out in the world, in Europe, mainly research institutes, and you can more or less build your own quantum computer out of it. It works at room temperature, and the fiber coupling can be done by butt coupling. So this is quite nice. Still, there's room for improvement, and I'm really curious to see the talk from Microalign later on, what the latest development is in terms of fiber coupling. So this is good, but can be better. Also, control electronics is a point that can be even faster, but there are good parties to cooperate here in Europe. Phase shifters is a different topic. So currently, this processor that you're looking at is working with thermal phase shifters, up to 50 kilohertz switching speed. And we would need for the fast feed forward faster phase shifters. And there are activities, we are also involved in a couple of them, in introducing lithium niobates, barium titanates, or aluminum nitrides or other materials into chips. Also, PZT is an option, so piezoelectric and electro-optic modulators would both work for us. We are following up some routes there in parallel, but it would be nice if someone of you has new developments, further developments on fast phase actuators. Would be nice to get in contact. So this is still an ongoing topic of R&D. So in 2020, we presented the first processors, these standalone boxes, where you can build your own quantum computer. If you have the ability, if you have the sources and detectors, this is more or less the Arduino in the middle that you need to build your own photonic quantum computer. In 2023, we built our first special purpose quantum computer. It will be cloud accessible soon. So this is just the processor plus sources and detectors in a nice 19-inch cabinet. And the power consumption is also very limited. It's mainly the cryostat for the detectors that you need. The processor itself, since it operates at 20 to 40 Kelvin, doesn't need that much power, honestly. So this is nice for data centers, just to put it aside next to their HPC. And these are activities that we are, for example, performing with QMware. So they will deliver an HPC. This will be directly next to this 19-inch rack. And yeah, the ultimate target is 2027, 2028 to have this universality, that actually a photonic quantum computer is able to deliver solutions for all kind of industry sectors and all kind of quantum application, running Shor's algorithm, Deutsch algorithm, you name it. And this will also have cloud access, this demonstrator. So this is the target where we're actually heading. I'll keep this a bit short, that there's room for questions. We have a great cooperation, great ecosystem here. There are a few locks here. So some of the partners I cannot name, but in terms of integrated photonics, we are working together with Laonix, Mesa Plus Institute, FIX, Pixel Photonics, and some others, which are under NDA. Software development, there's also a great ecosystem here in Europe, QC Design, QSoft, Quantify, to name only a few of them. Then platforms, QMware is our test customer for our cloud system. And of course, we are within the quantum computing initiatives from the German Aerospace Institute, from the DLR, where we are working on the first universal quantum computer. So, and we are in EPIC, in QPIC, in EFAM, QBN, and in QFOT, of course, as industry networks. Now, how was it called? The EPIC question. Let's start with what we offer. We offer quantum as a service. So if you have the interest in doing quantum computations, you can have access to our boson sampler this year. Also, we have rental systems. If you want to have a demonstrator in your lab, you can rent a processor, you can buy such a processor. Meanwhile, institutes also buy the processors to have a lab on a chip. So since this is a universal interferometer, you can do all kind of quantum experiments on the chip. So instead of buying 2,500 beam splitters, you can just buy a processor. That's quite convincing, some quantum optics professors currently. Components. So you can buy the processors, you can have it for loan, and also some demonstrators for single photon sources. We would be interested in collaborations. We are also active in standardization of the software stack for quantum computers, and on the roadmap, everything we need for the universal quantum computer. Since we are fabless, that includes a lot of components from fiber connectors to 19-inch racks and so on. So what EPIC can actually do for us, we are highly interested in assembly and packaging, especially mentioned a few times, fiber coupling of single photon sources. Every photon counts because it's information loss. And I have to pay this information loss with an overhead in sources. And this is really my pain point. So it's not that I cannot leverage this loss. No, I have to buy it, or I have to compensate it with a lot of overhead in sources. So that is really what makes the effort here. We are interested in use cases for photonic quantum processors and computers. So if you have a use case for an universal interferometer, let us know. High-speed electronics for electro-optic modulation is on our shopping list, as in SPDs for sure. High-speed ultra-low loss modulators, especially for photonic integrated circuit integration. This is something we are working on, but we are open to alternatives. There are plenty of ways how to do this. We have 3 or 4 under investigation, but feel free to contact us. And high-quality components, as mentioned before, and of course, inspection of PICs. And that was, I think, the last important slide. I will keep it short and leave some room for questions.
Thank you, Stefan. Great presentation, and thanks for highlighting exactly what you need and what you can offer to other EPIC members. So maybe we don't have time to go through the whole list that you have here, but starting with point 1, the fiber coupling. I think we already have a comment in the audience from Rolando Fiorini at Femtoprint. Rolando, do you want to comment?
Thank you, Ivan, for the opportunity. I wanted just to be sure to understand correctly the issue or need in fiber coupling, since it was mentioned twice in the last 2 talks. Once was on the materials, and then now on the, let's say, fiber coupling for single photon sources or for low loss. Since at Femtoprint, we produce 2D hole arrays in glass with high precision, submicron precision in hole diameter and positioning. And this is required, for example, in the world of telecom, datacom, in the transceivers world, for guaranteeing really high precision in alignment between the fibers and the devices. I was wondering if this is a similar need in the quantum when you say fiber coupling, or if this need is different. Because if that's the need, we can discuss what we can deliver. Thanks.
Yeah, so the target specification is definitely larger than 95% in fiber coupling from chip to fiber. So that's the target spec. And as mentioned before, if it's lower, then I can compensate with additional beam sources. But in the end, that drives the price, of course, and the effort in total. Fiber chip is silicon nitride, or in our case, triplex to a single mode fiber. And we would like to have directly arrays of 20 plus fibers attached to a single chip. So what we actually don't want to do is take a fiber and a very expensive 6-axis piezo manipulator per fiber, then do a 5-minute search, optimization, and then gluing per fiber. So photonic quantum computer will require 10,000, maybe also 100,000 of these fiber chip couplings. That's quite a lot. And therefore, it needs a scalable approach. So it would be nice to have some arrays that we can directly glue, so align very quickly and attach to a component. And this with higher than 95% coupling efficiency. It's doable technically and also in principle. So we can match very well the refractive index, and using tapers, we can also match very, very well the mode profile. So these two ingredients are there. The rest is really the assembly technology. So this is, I mean, single mode fiber coupling, when I started doing this 20 years ago, then if you had 60% in a fiber, it was amazing. And now we're talking about 95. So most of this is really engineering.
So just to complete the information, we currently produce 2D arrays of holes of hundreds up to thousands of holes with, if you take the diameter of single mode fiber, as I said, 0.5 microns precision in diameter and positioning. The assembly technology is put in by our customers. So if this is something of interest, we can discuss, and then I stop because there are others that would like to talk. I see Ligentech on.
Thanks, Rolando. Yes, so please address him if that sounds interesting. Yeah, Michael from Ligentech, please.
Yeah, thanks for the great presentation, Stefan. What are, for your ultra low loss modulators, what are your target specs for ultra low loss? Obviously, no loss at all is the ultimative target, but do you have a low number that is higher than 0?
Yes, probably in the region of 1/10 of a decibel per modulator. This is where we are. I mean, this is also realistic, or I can directly give back the question to you. Is this realistic?
Yes, I think that is realistic. So we're combining the ultra low loss of nitrides that you also presented that you're using nitrides and integrate different types of modulator architectures. And if you have such a hybrid platform combining, for example, lithium niobate with silicon nitride, you can get to transition losses that are in that range of 0.1 dB per transition.
That's sufficient. As mentioned before, we can lose a few photons, and the photonic quantum computer has the ability that I can also shift losses from some building block to another building block. So yeah, 0.1 decibel per phase shifter would be already acceptable if we have slightly better sources or something else. So within the architecture, we can move the losses a bit from A to B.
Okay, thanks.
All right. Is there any further comments? If not, I suggest we thank Stefan again for the contribution and everyone else for keeping the very live discussion. And with this, I'd like to announce the next speaker of the session, Simone Cardarelli, the CEO of Microline. And Simone will talk about the core-based fiber realignment for high energy efficiency fiber array-to-chip coupling. Hello, Simone.
Good afternoon, everyone. Can you hear me and see me, or at least see the presentation?
Yes, thank you, Simone.
Okay, then I will start from this one. Here we go. Okay, I can also see it. Okay, so this is the title. I will just repeat it of the presentation. It's core-based fiber array alignment for high energy efficiency fiber array to chip coupling. It's interesting that indeed it comes after these two presentations where fiber coupling definitely is a topic. A bit of an introduction about Microline. For who doesn't know it, probably nobody knows it because it's a very small and early startup. Microline was founded in 2021 as a spin-off of the Eindhoven University of Technology. We are located actually in the campus of the Eindhoven University of Technology in the Netherlands. And on the left here, you see a photo of the full team. Now we are basically 10 people, and we are closing our first funding round this year. So we are very excited, actually, exactly in this period. This is happening. Talking about fiber coupling and fiber array, let me express with this slide. Let me explain the motivation of the work of Microalign, where basically we find the problem. We understand from different interviews or analyzing the industry's discussions that, especially for, let's say, fiber array to chip coupling, there are like concerns or imperfections that could be solved in terms of best alignment, right? Because indeed there is a lot of work that it can be done, and that's be done in terms of spot size converters on chip and refractive index matching, for example, as it was mentioned by Stefan, in order to improve and optimize the coupling between the on-chip waveguide and the fiber. But there is also the need for many fibers. For example, I understand that in the case of quantum photonic computing, even 100 fibers could be connected in the future, and in the future, I mean in 1 or 2 years, to a chip in order to perform the quantum processing activity. And in case of 100 fibers, well, then the thing is that the standardly used technologies to make fiber array, which are usually based on V grooves, are, let's say, exhibit imperfections. For example, in the core eccentricity. So here I just show an example. It depends, of course, on the number of fibers. The core eccentricity can be, as a standard deviation, plus minus 0.5 micron. This can go up to 1 micron if we consider the full inaccuracy range. And basically all the effort, well, almost all the effort in optimizing on-chip structure or assembly procedure is lost in these imperfections, right? So this is the problem in terms of fiber array to chip coupling. Well, and for who this is a problem, here I'm probably also confirming this even more after the 2 initial talks. But here we see, for example, a schematic of a quantum photonic computer where I only focus and consider the quantum photonic part, basically the one with the interferometers. And what we understand is that the inaccuracies in standard current technologies for fiber arrays don't allow, for example, the photons to go from the fiber array to the chip, and to the chip to the fiber array again with the right efficiency that actually is required. And well, basically here we see an example with 120 fibers, 10 fiber arrays, and here on the right is just an example, let's say an exercise of considering 0.4% loss per fiber, right? And here I calculated just the probability for which all the photons go from one side to the other side of the chip. And you can see what I just want to show, and I think this is clear at this point, is that there is an exponential benefit or damage in having more or less photons, right? So considering the inaccuracy of the fiber arrays and considering what's the impact on this type of technology and considering what the industry needs, that's built the story to explain you actually also what we do. We thought, okay, if every fiber matter, well, every photon matters and every fiber matters, basically we thought, why don't we make some type of new generation alignment technology where actually we can align each fiber independently and at the same time, so that basically what we can prevent is the use of the problem of the individual fiber alignment, especially when many fibers have to be connected to a chip. What we see here is the front view video of a fiber, facet single mode SMS28, and in the blurry is one actuator, basically that is moving the fiber. So what we have embedded in Microalign is an actuator that can move at this moment up to 8 fibers. We want to scale it to many fibers, but the interesting is that each fiber can be moved with nanometer resolution and within a nice range. So what we see here on the left is basically how it works. The fiber will be pushed on an actuator. We have a comb of actuators, as we actually see also on the bottom left video. We have a combo of actuators. Each actuator has a V groove. So basically we can employ the passive alignment advantage of the V grooves and add actually active alignment per fiber best, right? So that basically each fiber can be optimally aligned. On the right, you see some quantitative measurement, which gives in terms of alignment range per fiber. It gives just an idea of what we can do. So each fiber can be displaced within a rhombus, which is 40 micrometers high, 40 micrometers large, wide, and each fiber can be moved with a resolution of 20 nanometers. So we have both, let's say, coarse alignment margin and high resolution possibilities. What you see here in the bottom left video, actually in this video, is one of our first videos. It's a 500 micrometers pitch fiber array. We very well know that we need to scale down the actuation range to, well, the pitch of the actuation to 127 micrometer pitch even. So the idea is that we want to use this actuator actually to make fiber arrays, and I will explain very soon how we want to do that. Here I show another video that basically it gives a 3D perspective of the actuators. On the bottom, so this is a 3D view of two fiber arrays which are butt coupled with each other. And on the bottom one, we see that the fibers are, it's nice that we can also see the red spots. It just gives the idea of how this should happen, right? So basically we have developed not only the actuator, but also a controller that can optimize the coupling, right? The transmission between one fiber and a chip, or one fiber to another fiber. But this gives the idea that the independent displacement is the potential, actually is our uniqueness. We can, now the fibers are manipulated one by one, but you can very well imagine that the uniqueness is that if we can manipulate all of them, we can make these fiber arrays in a practical way, right? Here I also show another video. This is how we want to use our actuation. Now you saw it from a 3D perspective, and here you see from a front view. So imagine it's a test video, so the ferrule is a bit damaged, but it gives the concept, right? Imagine that we have these ferrules with holes. The holes allow for actually allows the fiber to be manipulated within a certain range, and the concept is that we want to align the fibers thanks to our reference. It can be a chip or something else within the ferrule, and then basically fixing the fibers in positions once the alignment is achieved. This is still under development. Here I show on the right a concept 3D sketch of our fiber arrays and how the roadmap should be, and on the left actually what our steps to achieve these goals are. So our first goal is to have to realize the first 250 micrometers pitch fiber array by the end of summer, and then to scale it down with a core positioning accuracy of 0.1 micrometer, because basically this would go towards this, let's say, 50 millidecibel that people talk a lot about in terms of misalignment loss. And then we want to go to even 50 plus minus 50 nanometers pitch accuracy, and in 1 or 2 years the goal is to go to 127 micrometers pitch, because basically then indeed this fiber array can be used with the current designs, and you can well have many fibers close together. So this was the description of the problem, the solution, the technology, where we are now, what's the concept. I think that's my explanation for the moment. In terms of the call for action, well, first of all, thanks for listening to the presentation. But basically, if you have specific requirements or challenges that you want to discuss with us, we are of course very open to discuss. If you have questions on our technology, so that you can, for example, think, okay, we can discuss if the roadmap, your roadmap fits our roadmap, and we can talk about it and see what are the specific things to be developed in specific times. We will have our first samples by end of summer. I would be very happy if some of you could try those and basically give us feedback, or if you want to cooperate in projects, because I see that there is quite a wide applications of this type of fiber arrays for quantum computing, and maybe even more for different quantum computing features, technologies, but also for different quantum technologies. And here there is, well, just information about myself. Feel free to get in touch, and that's it. Thanks for the attention.
Yes, thank you, Simone. Well, we had so many discussions on the fiber alignment and fiber placement this time, and this seems to be just what the doctor ordered. So yeah, I'm sure there will be interest. So please keep the Simone's contact that was just on the screen. And do you have any comments for Simone? In the meantime, you said, did you mention so you can do this kind of alignment in parallel on several fibers yet, or is it something coming?
Yes, at the moment we can align already 12 fibers. At the same time, our next actuation technology will be for 24 fibers already. And it can be used for also, I mean, we will use it for fiber array because we think it's the easiest actually way to use our technology to get the benefit out of it. In the past, we also provided prototypes, alignment stages, but it feels like that the usability technical barrier is much less if we can provide already a fiber array which is just more accurate. So yes, but 24 is the first milestone in terms of the number of fibers. We would be already happy to achieve 127 microspeech with 24 fibers. But of course, the alignment stage can also be used, you can imagine, for testing or for 2D fiber arrays. So I'm very happy to discuss with the EPIC members afterwards.
Okay, that's very clear. Thank you. Well, if there is no further question, I suggest we thank Simone again for the great presentation, and we keep up with the program because the next speaker we have is Sara Purjamal, is a research scientist at VTT in Finland, and she'll talk about photonics for quantum technologies. Please, Sara, whenever you're ready.
Yeah, thank you, Ivan. So, do you see my screen?
Yes, just put it in the full screen mode, and the floor is yours. Thank you.
Okay, thanks. So good afternoon, and thank you for the opportunity to presenting VTT's activities related to quantum within photonics. And I would like to start with a brief overview of VTT's activities that is about low-loss platforms. So in VTT, we develop two different low-loss platforms, one based on silicon nitride and the other based on thick silicon on insulator, which is with the thickness of silicon of 3 micrometer. So I'll start with the silicon nitride platform. We are currently developing this platform with the current loss estimate of 0.5 dB per centimeter. But still work is in progress, so we would like to reach even lower propagation losses within this platform. And also, we also have a mature thick soy platform developed with the ultra low loss of 4 dB per meter propagation loss, which is built based on 3 micrometer thick silicon on insulating layer. So a brief introduction about the silicon nitride platform and the components, passive and active components at VTT we are developing. We are targeting applications within quantum sensing and quantum communication using this platform. Our current waveguide design covers wavelengths range of 900 nanometer to 1600 nanometer. These silicon nitride waveguides are thermally more stable, provide thermally more stable platform compared to silicon waveguides because of the lower thermo-optical properties of the silicon nitride. And on the other hand, we can also integrate like monitor temperature sensor as a ring resonator on the chip to monitor in situ temperature for the different integrated within different chips built on silicon nitride platform. On the other hand, it can be used as an evaluation platform for graphene photodetectors and modulators. We developed a wafer scale graphene photodetector fabrications with the with the detector responsivity with no bias of 1.8 milliamp per watt, and with the bias of 100 millivolt, we can reach responsivity of 700 milliamp per watt for these graphene detectors. So this can have applications as the fast detectors integrated within different quantum photonics platforms. So the other platform we developed is a TIC soy platform. VTT's TIC soy platform provides the possibilities for both hybrid and monolithic integration of active and passive components. We can benefit from ultra-low loss properties within this platform. Because of the thicker dimension of the waveguide, we have good mode confinement and less effect from the wall roughness and wall quality, waveguide wall quality fabrication on the propagation loss. So here are the different components and a sketch of different components we developed at VTT with the current performance of the waveguide and mirrors, detectors, and Euler bands. So this platform brings a unique opportunity and building blocks because of the very low propagation loss below 4 dB per meter and fast and responsive integration of detectors, and at the same time integrating of reflecting mirrors for broadband and polarization independent coupling to the different platforms integrated through, let's say, flip chip bonding or other techniques to our TIC soy platform. So I will give a brief example of one active component, germanium detectors we integrated on our platform. So monolithically integrated germanium detectors developed for quantum communication and quantum key distribution applications mostly, which are targeting high key rate and larger scale deployment. This platform includes monolithically integrated germanium photodiodes, responsivity in the range of 1 ampere per watt at telecom wavelengths. So we developed both high-speed PDs and monitor PDs, high speed with 40 gigahertz with when operated with 1 volt reverse bias and dark current of 4 microamp, and also lower speed with 1 gigahertz speed and dark current of 10 nanoamp at the moment. This is the performance of our detectors. And we are also doing cryogenic characterization of the performance of these detectors to figure out how they function at low temperatures. There is one use case application of this monolithically integrated germanium detectors for continuous variable QKD applications. We are developing balanced detectors on our TIC soy waveguide to be integrated within Lux Quanta's continuous variable QKD receivers. This use case is defined within QPilot project, which is a Horizon Europe project to establish pilot line services within Europe. Integrating balanced detectors, including hybrid 90 optics, is very important to get lower loss and better performance for these monolithically integrated receivers for CVQKD applications. Also, our in-house expertise in developing ultra-fast electronics and transimpedance amplifier design are used to reach the performance, the design performance in the range of 1 gigahertz speed for this in these balanced configurations. So integrating this with low loss hybrid 90 also gives better relative phase and time jitter compared to balanced detectors based on optical fibers, and in general it can be helpful to improve overall performance of the QKD systems. Other type of detectors we are working on are superconducting nanowire single photon detector SNSPDs, mostly for DV QK discrete valuable QKD applications. SNSPDs are used to, as you know, to receive quantum signals transmitted using, in this case, DVQKD protocol. Implementing in this central node configuration, we can do hybrid SNSPD integration on our SOI platform using high precision Philip chip bonding. Here is a 3D sketch. Our solution for Philip chip bonding of arrays of SNSPDs within our low loss within our low loss silicon uninsulating platform, which gives also higher fabrication yield to do this integration in two different platforms. We can run in parallel fabrication run for the waveguide part, and also fabrication for the SNSPDs. And then at the end, using Philip chip bonding and especially benefiting from a polarization independent upreflecting mirror, we can bond these two chips together and couple single photons or Gaussian states to arrays of SNSPDs. And also we developed arrayed waveguide gratings to demultiplex WDM signals coming from single fiber and couple them to SNSPD arrays. In this hybrid approach, this is part of a Cryocom project, and we got test SNSPD arrays from single quantum, and we integrated it within our TIC-SOI platform. Also, in parallel, we are developing our own SNSPD fab runs. We have a niobium nitride SNSPD fabrication, and also we are developing a wafer scale process for amorphous superconducting molybdenum silicide in our co-sputtering, using co-sputtering techniques. MOSI deposition is developed and different ion bombardment techniques like gallium and argon has been tested on it to test the amorphization effect of different ions to lower to improve the superconducting transition temperature and the superconductivity performance of these MOSI films on a wafer scale. And this is still work in progress, and we are collaborating as part of different projects to improve these fab runs. And as the final note, I would like to take also the opportunity I mentioned that VTT is coordinating a quantum pilot line project in collaboration with several RTOs across Europe, TNO, IMEC, Fraunhofer, CIE, and several other pilot lines that you can see in the figure here. So the goal is to develop a sustainable ecosystem to provide pilot line services for European companies, startups, and SMEs active in the field of quantum. We also part of the QTest project. So the idea of these two projects is to develop fabrication pilot line and also test line for quantum technologies across Europe. So within these projects, we are launching open calls, which is interested for European companies, SMEs, startups. So we highly encourage European companies to keep in touch with us and check our webpage. So the call will be launched in June, and within this call we will get several use cases depending on the needs from different companies. We have the technologies to be offered. You can find them in the webpage. And within this project, all the companies will get, selected companies will get 100% subsidized services from the pilot lines involved in the QPilot and QTest project. And specifically, we have Photonics platform for quantum technologies, which would be very interesting for the European companies active in the field of quantum photonics. Thank you so much for your attention. It was all from my side about VTT's activities.
Thank you, Sarah. It's a very comprehensive overview, and yeah, it's actually fascinating to see how many things VTT is involved in terms of quantum technologies. Yeah, I mean, you covered so many topics. Is there any question or comment from the audience? Okay, we have Jorn from Epiphany. Please go ahead.
Just one question about the SNSPDs. Are they compatible to waveguides also, or just as layers?
They are. We are developing in parallel this monolithic integration on our platform. But the more mature ones we have is like hybrid integration using upreflecting mirrors. But we are also in parallel developing process both on silicon nitride platform and our TIC soy platform to integrate these SNSPDs within the waveguides.
Yeah, exactly. Yeah, it would be nice to have one platform, right, where you don't have to go even off chip.
Yeah, exactly.
Yes. Thanks.
Okay. Yes, and thanks also, Sarah, for highlighting this the pilot line and the open call that is upcoming. I think it will be very interesting for many of our EPIC members. Any other questions for Sarah? If not, I suggest we thank her again for this wonderful presentation. And last but not least, today we have a presentation from Eric Mounier, the chief analyst from the Yole Group, the famous technology market analytics. And he will talk about photonics as an enabling technology for quantum computing. The floor is yours, Eric.
Thank you, Ivan, for the introduction and the opportunity to present our latest funding into quantum computing with a focus on photonics, of course. So briefly, today I will present an overview of the quantum computing application and ensure status. Then, of course, I will present some market application forecast, and I will conclude how photonics can be a very important enabling technology for quantum computing. So, first of all, quantum is real because at every level of the supply chain, there are companies involved in quantum computing development. We start, of course, with the quantum hardware layer, but also some company doing quantum computers, some company doing software application layer, services layer, and end user layer. And at the moment, it's not very clear what will be the first use case for quantum computer. But on my side, I see quite important traction for finance application, medical, and industrial applications. And also another very interesting things I've noticed since the past month is that some big semiconductor companies are now looking at quantum technology, either by providing some foundry services, like for example, Global Foundry, or by providing some test equipment, tool equipment like Keysight, for example, for testing quantum chip and quantum systems. Of course, you can see here some big names like Intel, Honeywell, like Google, but in Europe, we are very, very strong player involved in quantum, not only photonic quantum computing like Quantela, but also technology as well. So just a quick reminder, there are different types of quantum computer, and we are quite far from maturity at the moment because, of course, with the long-term development. But here again, what I've noticed since the past years that there is no real quantum winter. I will show afterwards some level of funding for quantum technology, and it's interesting to see that every month there is new funding routes for quantum technology, and most of the funding is for quantum computing at the moment, and even new startups are created. So today on the market, we can find quantum annealer based on superconducting qubit or quantum emulators. We are now entering the era of NISQ, where we can use a few hundred of physical qubits, which are better performing than HPC, but still limited by noise. And before having real use case, which takes still a few years, but actually I visited some interesting quantum company in the past month, and it's moving quite fast. So probably before 2030, we can see the first practical achievement of using quantum computer. And of course, in the long term, we'll see a universal quantum computer. So of course, we need a high number of logical qubits. It means a high number of physical qubits, and it will be a 10 to 20 years more development. All these quantum computers are based on different platforms, qubit platforms. The most famous ones are superconductor, photon, spin qubit, quasi-particle, NV center, trapped ion, and cold atoms. Here, that's a roadmap of some company developing qubit technology. So you've got many names and many companies. You can see that over the past few years, there have been quite speed up into the achievement of a number of qubits. For example, Quandela in France now has optical quantum computer using 30 qubits and it's based on PIC. There's of course PsiQuantum developing a PIC-based quantum computer, but they plan to achieve 1 million qubits. We cannot say when, but at least it will be the first real photonic-based quantum computers. What is interesting to see that if we look at the level of funding, of investment, private investment for the different platforms of qubit, it's interesting to see that actually most of the funding is currently for photonic platform. Of course, it's mainly due to a big company, PsiQuantum, that attract a lot of funding, but with also at Xanadu in Canada, Photonics Incorporated in USA, Turing, Quandela, QSI, that have raised funding for photonic based qubit for quantum computer. Of course, one of the most mature technologies still attracting a lot of investment is superconducting qubit on the left of this graph, with historical players like D-Wave. Of course, one of the champions of quantum computer is IBM, which every year achieve a new step in their roadmap, and is based on superconducting qubit. There are some other challenging technology, like, for example, a trapped ion, neutral atom, or something with coming now, it's a quantum dot spin, silicon spin-based qubit, with just coming now with interesting development. So interesting startup in France, for example, C12, using carbon nanotube or Cobley, latest spin-off of CLAT, that start attracting some funding. One of the advantage of this spin qubit technology is, of course, the scalability, because we could use CMOS processing to achieve a large number of physical qubit, and after that, a large number of logical qubit. But scalability is also a big advantage of photonic IC, because here we also use wafer scale technologies. So this is a difficult exercise, but if we try to make a benchmark of the different qubit technology, we can see that no platform is perfect. We can say this one is better than this one isn't good, this wasn't, but everyone has his own advantage and disadvantage. For example, if we look at superconducting, of course, we got the good scalability. Today, this is a platform that achieves the largest number of qubits with high IBM, but the coherence time, T2, is not so good. On the other end, if we look, for example, for spin quantum dot, we got very tiny qubit, so it's cool for scalability. Here again, we can use CMOS process, so we can scale in millions of qubits, but in terms of achievement, probably it's the platform with the lowest number of qubits today. And because we talk about photon today, if we look at the photon platform, it's a bit difficult to compare photon to other qubit platform, because actually we can consider photon like flying qubit compared to cold atom, trapped ion, vacancy center, superconductivity, and spin qubit. But one advantage is first, we can use photonic qubit at room temperature, which is a big advantage because we don't need very expensive and bulky cryogenic system. It's of course a scalable platform using either, for example, silicon nitride, which have a nice maturity in manufacturing. We can achieve PICs and achieve the realization of QPU based on photon. But here, in terms of achievement of a qubit, we are still maybe in a low number. At the moment, Quandela achieves 6 number of photon qubit at the moment. Here again, it's very difficult to say, okay, this platform will be used in the future to achieve quantum computer. Probably it will be a mix between different platforms. Again, one nice advantage of photon here is we can use photon to interconnect, because there is a lot of know-how in datacom and telecom using fiber optics to interconnect devices together. So one advantage also of photon is not only the realization of the qubit or the processor unit, but also all the interconnect of the computer or the different system together. And it's also interesting because we got one mature manufacturing platform with this silicon photonic. So it can be SOI based, silicon nitride. Over the past year, I've seen that we move from SOI, pure SOI technology to other type of material, still wafer scale, but still using silicon, so like silicon nitride. But step by step, I see also new material coming to be integrated on this platform. We mentioned, for example, film lithium niobate for modulation, which is also very important because high-speed modulation will be key in quantum computer. So if we can have specific material can be fully integrated to the manufacturing platform, that will be really an advantage. But here, silicon photonic platform is interesting because it leverages wafer scale simulation manufacturing platform. It's a product success and maturity because today we ship millions of optical transceiver by Intel, Cisco, and a few others based on silicon photonics. We cut an existing foundry infrastructure with mature process, and beyond interconnect and optical and for the qubit, there's also interesting development into pure optical computers. So here I come to this slide that shows the different architecture for the main 4 types of quantum computers. And you can see that photonic can be used in almost all of them. I could add that for superconductor qubit, they use microwave and quantum chip based superconductor. We can even imagine using photonic for interconnect. But for all the other trapped ion, cold atom, or photon qubit, there's at least 2 photonic or optical systems, either to control the qubit, control computer with laser or spatial line modulator, or to trapped atom with optical tweezer, or to make the qubit read out, or to make the photon detector, or to use a unique photon sources. And of course, the qubit chip by itself can be an optical chips. So you can see that photonics, whatever will be the different architecture of quantum computer, will play a role in that. And for example, Optica gave a presentation. Our laser is an embedded technology for quantum computer. We could also need some PICs based on silicon nitride, for example, to make the quantum optical chips. We need sources, we call single photon sources or photodetector, different material. Also, it's interesting to see that for some architecture, trapped ion or cold atom qubit computer, there will be more or less the same electronic optical setup. You see for trapped ion and cold atom qubit, we will need some optical system to control the qubit with laser. We will need spatial light modulator, CC readout, and also we will need laser to control qubit and to make the readout. Or also for cold atom qubit, we need laser, mini laser, and a digital mirror display to trap atom to control the qubit gate or to make the qubit readout. So there will be no quantum computer without photonic system inside probably in the futures. So actually, it's an industrial reality, quantum computer, but it's also an existing market. This is a 2022 player market share involved in quantum computer. So I do not say this company is making money by shipping quantum computer, but when you look at the revenue, actually they declare some revenue based on NRE or R&D project or a specific project. So got Rigetti, IonQ, for example, and many other small players doing custom writing project and having some revenue from that. So the forecast I did for quantum technology. So quantum technology is not only computer, even if computing is always the largest share, but quantum technology, at least using photon, can also be linked to communication with cryptography or to sensing. But if you look on this bubble for 2022, 2025, and 2030, you will see that the largest market growth will be the pink bubble that will be for quantum computing. And I distinguish two things, hardware and quantum as a services. So what I call quantum computer full stack is company that will deliver complete quantum computer. But they will be very expensive and bulky system. For example, Quantum is currently developing a huge quantum computer, and it's unlikely they will deliver 10 of that. Probably they will have specific business model to run some calculation services as some data center already do. So quantum as a service will be what you will pay to use quantum computing to make modelization, simulation, for example. And and company will get money for that from the time you will run to them to make your calculations. Okay, so this what you can do for us, what we can do for you. So we don't do any hardware, so we are a market research company, but we are always happy discussing and interacting with you to exchange my vision of the market with you, to keep update of your latest achievement, just to be on track on the quantum computing evolution and to share my analysis with you. So thank you for your time, and you got my email address if you want to contact me. Thank you again.
Thank you, Eric. Very inspiring talk and a lot of insights. So indeed, feel free to reach out to Eric directly or through us, Epic, and we'll be happy to put you in touch. Indeed, I mean, so many insights in your slides. Does anyone in the audience have a comment? This is the last talk of today's session, so we can also keep it a little bit less formal now. Do you agree with Eric on all of those projections, or any objections maybe? It was actually, for me, it was very interesting to see the comparison with the other non-photonic technologies, or the technologies that only partially use the photonics approach. Okay, so maybe a comment from Luca, European Commission.
Quick question.
Yeah.
In a scale 1 to 5, how independent is European Union from the raw material to the quantum computer, according to your vision?
I don't think it's critical, actually, first, because there will be not millions of quantum computers. And so it's not like consumer or even automotive or doing battery for electrical vehicle where we are really dependent of exotic material. Here, in terms of material, of course, we need material for laser. There are already some good laser company in Europe, like Toptica, for example, that do laser for quantum. In terms of silicon, here again, we got silicon foundry in Europe, or we can also outsource to some US company like Global Foundry that can supply some photonic chips. And we mentioned lithium niobate, but lithium niobate is already used in large volume for telecom. And what I see is the use of lithium niobate is a thin film material to be more easily integrated into a photonic quantum chip. And here again, we got some company and foundry in Europe and Switzerland, for example, that supply thin lithium niobate foundry services. So honestly, I will put maybe one. Maybe I never identified any critical issue regarding raw material for quantum computer at the moment, because as I explained, the material are quite common, I would say, in semiconductors, and Europe get that. And it's not millions of units. Maybe there will be hundreds of quantum computers worldwide in short to medium term, and I think we got enough material and capacity. I don't know, maybe I'm totally wrong, but for me, that's my opinion, actually.
Thank you very much.
What is your independence score again? Is it 1 or is it 5?
Oh, that's 1. So low, I mean, means low, not 5. No.
We are quite independent, you mean?
Yeah, I mean, okay, quite independent. Yeah, that's what I mean.
Okay, thanks for this answer. Now Andreas Volker from CSEM.
Yes, thank you for mentioning us in Switzerland, outside of the European Union funding schemes for the moment, but happy to rejoin anytime. Yes, we have a foundry for LNOI in Switzerland. We actually have other suppliers also arising, besides CSEM, also based in Switzerland. However, the wafers itself, the thin film lithium niobate wafers of high quality, are as of yet only scarcely available from European sources. So here we still have a challenge. It is still China that provides the top quality and the greatest variety and the greatest quantity. So here there would definitely be a challenge if we see that lithium niobate, and I'm talking always thin film lithium niobate, becomes an important player, not only for quantum computing, but also for telecom, of course, datacom. Because of its modulation fees, then we do not have as of today, the capacities and quality maybe we would want for this situation in Europe.
I fully agree with Andreas. I think that's the weakest link.
Eric?
Oh, if you want me to comment, I agree for wafer of lithium niobate, but I think some company are processing thin lithium niobate on glass wafer or silicon wafer. So in this case, it wouldn't be an issue if we use thin lithium niobate. I'm thinking of companies like Hyperlight, for example, in the US. I think they use semiconductor substrate, not lithium niobate substrate.
I mean, we're talking about thin film on silicon wafers. They're also buying it from China.
US is not the European Union, please.
Sorry about that. Yeah, I agree.
Okay, so there are possibilities, it seems. Do you agree, Andreas, or not?
No, I don't see at the moment that we have anything comparable to what is in that quantity that is available from China. So China is clearly leading here, and there is if I'm not so concerned about this, but if we're talking about sovereignty Europe, as a critical supplier, we may get in the situation again that China invests in the quantities and then has the lithium niobate thin film technology at a level that makes it impossible to compete with prices anymore from any European supplier, and which would be good. Maybe we get that. Also means that we get cheap photovoltaic units. It may mean that we get cheap lithium niobate from China, but if we want to be sovereign in this case, there's of course a danger that we run in this, that we have missed the possibility to have sufficient capacity at an early time, and then it's very hard to catch up to this.
Okay, that's a good estimation. But yeah, let's give the right to say something to maybe Stefan from Quick. Do you have a comment on this?
Yeah, not from Quick, but from Quicks. I just wanted to add something here on the European sovereignty. So maybe as good news, our first special purpose quantum computer, our boson sampler, completely is based on silicon nitride. And therefore, we have the foundries here. However, I mentioned in my talk, we have to add some additional materials that can be some niobates, but also some titanates and so on top. And there are also alternatives to processing a full lithium niobate thin film wafer from, I don't know, NanoLen or wherever you buy it. So what we can do is we can reduce the amount of lithium niobate by transfer printing, by heterogeneous integration of things. So, I mean, this goes exactly into the direction that Eric was pointing. There are possibilities to reduce the influence. So we do not need a full lithium niobate wafer and make everything one size fits it all out of lithium niobate. So we still have silicon nitride. That's a great platform. And maybe we should be also a bit more bold that we have something in Europe. I count also Switzerland to Europe. So greetings to Legion Tech. I see them also as a very valuable partner here in this eco chain. So let's not focus on what the Chinese have. Let's put a bit more effort in what we have in Europe, and maybe it's not a 100% copy and paste. It's a bit more looking in depth into what building block of the quantum computer needs which specifications. And our approach is the world is hybrid. So there are some indium phosphides, there are silicon nitrides. You need probably 3-5 materials to be integrated. So it's not pure lithium niobate, although it's of course an important material for the future.
I just wanted to add to that. I fully agree with that. So I didn't want to imply in any way that thin film lithium niobate will make or break quantum computing. It's one of the components that if it plays any role, there we have a dependence. And far more than in other cases. But luckily, as you mentioned, Stefan, it's true. We have alternatives, and by no means is it determined yet that thin film lithium niobate is crucial.
Amir, do you agree?
Yeah, I just wanted to add this. So, we have to look at it broader than the quantum. Again, the consumption at quantum is sort of fractional, but sort of we are talking about a greater photonic integrated ecosystem, which quantum is only a part of it. Yeah, I mean, the consumption, we have probably enough sources for that. But if you include telecom and datacom, then this is where we actually have the real problem. And no, we cannot get away with it without actually having a European source, or let's say a Western-based source at least.
Okay, maybe if that's clear now on the lithium niobate side, just to change the topic for a little bit. So Stevie from TII Institute in Abu Dhabi. Sorry for keeping you wait. Do you also have a question for our speaker? Just unmute.
Okay, all right. Yes, thank you for the presentation. It was very interesting, Eric. I have a question for you. In your first slide, you clearly mentioned the fact that it's not so easy to compare the Photonics solution compared to the other platform for the computing. So I would like to know from your point of view, what is missing currently to have this bridge, to have a clear view on how to compare the performances between those technology, between the Photonics technology compared to the other technologies?
Well, it's a very technological question, but the fact that I have mentioned, for example, because even in terms of size, because photons are flying qubit, first it's very difficult to compare them with, I would say, solid-state qubit based on silicon superconducting. And also, we are at the very early stage of quantum development, so performance will still improve. Nothing is fixed yet. Even the number of qubits you will need to achieve a universal quantum computer is not fixed yet. How many physical qubits will be needed to make a logical qubit? It's not. Things are every year improving. So we can compare qubits one to other. We compare the coherence time, lifetime, accuracy, and so on. But I would say that's maybe it's not an issue what is missing. Just that today, every year we see new improvement into performance qubits. So things are still moving. And again, photons are quite particular qubit because they are not solid-state qubits. So that's what I mean here, actually.
Okay, I see. Maybe in about of quicks, they could answer. We could have an answer. I mean, I was already wondering because actually, it's right that if we more talking about Q mode, maybe here is the bigger answer to try to see to leverage on all the degree of freedom of the photon to really have a more let's say taking into consideration all those degree of freedom to compare really what we could do as a let's say as a rainbow of axes compared to what we could do in the of our platform. I think that up to now you're more looking at the special Q mode, but if you compare even with some work that was done using optical comb frequency that allow to have squeeze state on many frequencies, so maybe here we start to have a more bigger let's say number of mode as well.
Maybe I should answer directly yes. So photons offer the possibility to encode your qubit in different ways. I mean, in the end, you have to, because a photon is not a two-level system. So you have to think about a metric, and the easiest way is dual rail encoding. I mean, Eric had in his table, I think, the 6 qubits from Candela. That means if they do dual rail encoding, they have 12 input ports. If they work with squeeze states, then they have probably 6 input ports. We see here there's already a difference how many channels, input ports, fibers, and sources I need for different ways of computing. I see with the squeeze states, I want to be fair with all these approaches. One of the biggest advantages of GKP states or squeeze states is that you in principle can do analog quantum computing with those better than with single photons. However, for the sake of easiness, I see that the first photonic quantum computers will be with single photons. That fits just better to what we have on the table currently in terms of sources. Xanadu is still approaching the squeeze states. Let's see. The good thing is we can switch quite quickly. It's still, it's ring resonators, it's Vernier filters, it's all integrated photonics. And and I agree with you, that's the additional degree of freedom. To change the way you encode your qubit, maybe we figure out in 5 to 10 years that one of these ways is better by a magnitude of order in error correction or something. Then we can quite easily switch to a different architecture. So far, it's an open race in an open race, I would say.
Okay, gentlemen, thank you for running this discussion, and it's indeed very there is a lot to debate about. We're just hitting now the limit of our time. So let me just do a quick wrap up. And after this, actually, you're all welcome to stay for an informal discussion that is not also recorded anymore.